Hey, Vlad here, devinsideu.com. Welcome to another video. In the previous video, we talked about the stacks, which are a prerequisite for one of the advanced tail call elimination techniques, which we're going to be talking about today. And we have a lot of code to write, so let's get started. As always, we're in the Ubuntu virtual machine, and we used to run Sublime at the top and the regular terminal at the bottom, but I recently made a video about the wonderful plugin called Terminus for Sublime Text that can emulate the terminal for us. So now we are running just Sublime, and at the bottom we are running Terminus with SBT inside of it, and we run the test. Every time we save the file, the test will be rerun by SBT, the same as always. Alright, today we'll begin this video with a few refactorings that are completely unrelated to the topic. This is something that I sometimes do, when I come back to work, on the next morning, and then I see what I did, the day before, and then I try to improve it a little bit. For example, I was explaining to you the right associativity of the methods that end with a colon, and I forgot to remove this method, so I'm just going to remove that from the stacks. The next thing that we're going to do is we're going to go to the tree suite. Right? And we're going to find in the line 7 we have a print line. So if we scroll into the test, there will be somewhere a line of hyphens over here, and this is what we don't want to have. Let's remove that. All right, let me scroll back down over here. There we go. Come on, compile, run. All right, there we go. The next thing that we're going to do is we're going to go to the set suite, and I found a yield mistake over here. Yield. There we go. All right, the next thing that we're going to do is we're going to go to the sets, and everywhere where we are creating a non-empty node like this out of an existing node, which is over here, instead we're going to use a copy method defined on case classes. So non-empty is a case class, so instead of having this line, we're going to say, okay, so this is whatever it was before, right, which is this one, non-empty, right? And we're just going to copy, and if you notice, the element stays the same and the right branch stays the same, but we're changing the left one. So we can just say, okay, the left one is going to be left.add input, right? So, and if I do that, because we have tests, they will tell me if I made a mistake or not, right? And now the same thing at the bottom over here. This is going to be right, and that reads a bit more nicely. So I'm just going to keep doing that with these. In fact, I can just copy that and put into the remove and say that this is going to be, where is it? Here, remove, and this one, remove. Should be good now. Whoop. Oh yeah, I forgot to copy that part. There we go. All right, let me scroll down. I believe that's actually it. Yeah, I think that's all we need. The one in the add and the one in the remove. That is, yes, that is all we need. One last thing is that when I was working on this video, I realized that sometimes I would make some changes and I would introduce a mistake, but the tests were still green, which is a clear sign that a test was missing. So I found the test that was missing, and it was one of the tests for the addition, and I'm just going to paste that over here. And what it's testing is that when we add the same element twice, the element that we're trying to add again should simply be ignored, right? So we're creating a random first element and the second one, making sure that they're different. Then we are creating a side with first, second, and then second again, and then we're making sure that it's the same as the first and second, and also we're making sure that the size is 2. And then we're doing the same, but instead of adding the second element again, we're adding the first element again, right? So now we have the first element twice. Over here we have the second element twice, and the results should still be the same. So if I just add it now, it will still be green, right? Because we don't have a mistake. And there we go. Everything is still green. So this is all that we need for today. Let me actually exit SBT, and I'm gonna do git status. Yes, we changed a few things. There we go. Add them all. Commit -am, and we're gonna say that this is a video 13, and this is just refactoring and other improvements. And there we go. This is all we need. Let's go back into SPT. We're going to push by the end of the video, and let's keep running our test the same as we did before. And there we go. We're back to normal. All right, so since the topic that we're going to discuss today is a bit more advanced, we're advanced, our topics get more and more complicated. We're going to start with an example that is unrelated to our sets. We're going to start with an example which is fairly well understood, and this example is Fibonacci. So I'm going to exit from running the test, and I'm just going to keep running the main that we don't even have yet. So what I will do is I will create a file called over here. Let's just pretend that it's in the collections library. It doesn't really matter because we're not going to commit it. So I'm going to create it. I'm going to call it Fibonacci. That's Scala. I'm going to copy Fibonacci, right? So we're going to create an object, Fibonacci extends app over here. We don't need that anymore. Print line my 50 hyphens. So hyphens time 50. Oops, that should be times 50. Let's have it twice over here, and let's print line a hello world so that we see that it's working. Also, let's be in the same package just in case if we, if I'm going to switch to using our collections library. So homegrown collections, okay. And remember the video that we did about rendering trees, and we discovered that there's a fancier hyphen, and I believe it was the Unicode character 2500 if I'm not wrong. Let's see. Yeah, so see, these hyphens look much prettier than these ones. In fact, now I can just copy it and put it over here instead. So see, it's a different hyphen. Right, so now our print lines, now our main method is going to be better delimited, which is kind of cool. All right, so we're going to have the Fibonacci function, which everybody knows by now. We have introduced it in the video about recursion a long time ago. So it gets a number and produces a number, and this is the naive implementation. There are a few versions of Fibonacci, one that starts with a 0, the other one that starts with a 1. Else if and equals 1. And by the way, we switched to a Fira code in the previous video in case you missed it. This was also the same video where we introduced terminus, and because I believe that we can benefit from it. So this is pretty much the definition of Fibonacci. We're just adding together the previous two numbers, -1, -2. Okay, so let's have a tiny example where we have 0 to, I don't know, 10, map to Fibonacci, and for each print line. And if I did not make any spelling mistakes, of course I did. What does it say? Required int. All right, so let's map them to long. There we go. What's happening? Oh my god, I'm not awake yet. All right, let's map it again to Fibonacci. All right, there we go. So this is a Fibonacci sequence: 0, 1, 1, 2, 3, 5, 8, and so on. So what we're going to do now, like even though I've showed you a long time ago that we can rewrite Fibonacci in a way that is tail recursive, what we're going to do now is we're going to pretend like this was not possible, and we're going to move the computation to the stack, and then we will understand how it works, and only then we will switch to the examples in the sets where it is actually not possible to write them in a tail recursive way, and over there we will actually use the stack. So the way we do this is by first rewriting the Fibonacci example into this. So I wanted to say the so-called canonical form, but in fact I call it canonical. I'm probably the only person who does that. Okay, so what we're gonna do is we're gonna call this one. I'm just gonna copy that. I'm gonna call that Fibonacci original, and now the code is not gonna compile because we're still calling Fibonacci here. All right, so I'm gonna go here. I'm gonna paste that, and I'm just gonna keep calling it Fibonacci, and this is the one that we're going to rewrite. Right, so we're going to rewrite it pretty similar to the way we did it before. We're going to rewrite it with a loop. All right, so we're going to have the loop, and the idea is that this loop is going to be tail recursive, right? So we have the annotation.tailRec. Okay, so the loop is getting the x, which is long. It's getting the ACC1, which is long, ACC2, which is long, and it produces a long, and it does the same thing as it was doing before, like that. Let's move it to the right like this. Okay, so instead of Fibonacci, it will call loop here, loop here. We're gonna call the whole loop over here was n, 0, and 1. Okay, so in the default case, we're just going to return the first accumulation, and in the second case, we're going to return the second accumulation, and obviously this code is wrong now. Okay, so the whole idea is that we're calling a loop not only once, but only in the tail position, right? So the last thing that can happen here is either already an evaluated result, or we're calling the loop. All right, so we have the tail call. Okay, so we have x minus 1, ACC1 becomes ACC2, and ACC2 becomes the sum of both of them, right? So if I didn't make any silly mistakes, then everything should be fine. And notation, I always do this, I don't know why. Right, so this is the tail recursive version of Fibonacci, which I screwed up, obviously, because it's now in an infinite loop. Let me check this out. Oh yeah, I'm still using n instead of axis. All right, there we go. Okay, so now I have to kill it, start SPT again. It should be fast. Run the code. There we go. Come on, it's not that much to compile. There we go. Okay, so it's still the same. So what we're going to do now is we're going to take this form and we're going to rewrite it in such a way that it will use a stack instead of just one long. Now the thing is that this one long is enough because we're only pushing things to the stack, right? So we're only going forward, which is why there is a tail call. I'm sorry, a tail recursive version of it. But if it wasn't, then we would have our own stack, and we would manipulate our own stack. And sometimes we would push things on the stack, and sometimes we would pop things off the stack. Now, in case of Fibonacci, we will not pop anything. We will just push things. Okay. So what we're going to do now is, again, I'm going to copy that. I'm going to call this Fibonacci tail rec, and I'm going to add it over here, right? And instead of x long, we're going to be using a stack. Right, the stack that we wrote in the previous video. Okay, so now we have the stack, and now we somehow need to get access to this x. Right, so in the beginning, what we're going to do is we're going to have the x, which we're going to take it from the stack. So the thing that is on the top of the stack is the current x. So we don't need to pop it. We just need to peek into it. And if you remember correctly, peek returns an option, so we can get it out. Now, .get throws an exception, right? So x is along now, by the way, right? X is along, the same as it was before. So .get throws an exception, but because we're never going to pop the stack will never be empty, and therefore there will always be something in there. So it's fine. Okay. So now we still have the x, and what we need to do now, instead of just doing that, we need to push something on the stack. So I'm going to leave that line over there for a second. I'm going to say stack equals stack dot push. And the next x is going to be x minus 1, right? So it's virtually the same line as over here, but instead of using one long, we're using an entire stack, and we're acting as if it was really, really necessary, right? So I believe that this is almost everything that is that we need. The only thing that we need in the beginning is to actually push the x onto the stack, right? So we're going to start with an empty stack, and we're going to push the n on it. And unless I made some silly mistakes, it should be fine. Yes, it is fine. Before we continue, let's examine the original version of Fibonacci and try to figure out why there was a tail recursive version of it. So over here, there is no tail recursive version because over here we're pushing something onto the JVM call stack, then we're coming back, so we're popping the stack eventually, and then we're pushing something on it again. So every time you have a pop and which is followed by a push, you know that this is not in this is not in the tail call position, right? But once we refactored that, we only had pushes, right? We only pushed on the JVM call stack, which is this loop, and once it was popped over here, there was nothing else left to do, which is why when we did it ourselves, we only see one push. I mean, this one, we can ignore this one, right? There's only one push. It doesn't matter if we had multiple pushes. The only thing that matters is that we don't have a pop, which is followed by a push. So what we're going to do now is we're going to switch back to testing, right? We're pretty much done with Fibonacci. We're going to open our sats, and we're going to look at contains. And contains happens to be already tail recursive. Why? Because over here, I'm going to add some comments. We're just popping the JVM stack over here as well. Over here we have the JVM push and pop, right? So we're calling contains again. So we're pushing contains again on the stack, and then eventually it comes back, but there's nothing to do. So there's no push that is following a pop. And the same thing over here, JVM, push and pop. Just gonna get used to using two of them. Now we're gonna do the same thing for contains as we did for Fibonacci. We're gonna pretend as if it wasn't, you know, tail recursive already, and we're gonna rewrite it into this canonical form so that you kind of get used to this almost mechanical transformation, right? So I'm gonna copy that. I'm gonna call that contains original, and because it's not an override anymore, we're gonna do that. Okay, so I'm gonna paste it over here. Let's just see if it still works, because I didn't really change anything. All right, so the way that we do this is the same as before. So instead of just calling ourselves all the time, we're gonna have a loop that will do this for us, right? So we're gonna have the same as before. We're gonna have a loop over here, and we're gonna pass it the sat. And in the beginning, I'm gonna also start writing it over here. And the beginning, we're just calling loop was this, right? And therefore we're passing this as a sat, and therefore we don't need to match on this, we need to match on the sat. I'm sorry that I'm writing this like a little bit here, a little bit there. I think it's gonna be more, you know, more clear like this. Now, usually with sat, you know, and not with sats, with these tail recursive structures, we have some sort of accumulation, right? And what we're accumulating here is a Boolean. And in fact, by the end of this implementation, we will see that we're actually not using this accumulation. So I'm just going to leave it like this, comment it out, just as a sign that this is exactly why it is already tail recursive, because we don't need to accumulate anything, right? So loop returns a Boolean, same as before, scala dot annotation, come on, annotation, come on, tail rec, okay, there we go. Now all we need to do is to move this whole thing over here, and let's see. Oh no, I'm still calling left contains. Hold up, we can't do that. We need to call loop was left. The input is already in scope, right? So we don't need to keep passing it around. And over here we need to loop right. There we go. Yeah, so now it's still green, right? And also, because we're going to be dealing with sats and with stacks, I'm going to start doing this. I'm going to start doing set.empty. What is happening today? Set.empty and set.NonEmpty, and this way it will be easier to visually distinguish sets from stacks, just a little bit. All right, so as you can see, our test is still green, and we did not need any accumulation. All right, therefore we know that it was tail recursive before, and it's still tail recursive. So we're gonna do the next step now with our own stack, right? So we're gonna copy that. Contains, I'm gonna call it contains loop. Doesn't really matter, and it's not an override anymore. Come on, there you go. Let's go here. We have our contains again. Okay, so now we just need to rewrite it with a stack. Before this, let's just go back to Fibonacci and look what we did there. So even we said that even though it's enough to just have our long, we're going to replace it with a stack, and we're going to do the same thing over here. Even though it's enough to have this just a sat, we're going to replace it with a stack of sats, right? So instead of the sat over here, we're going to have a stack. It's going to be a stack of sets of elements like this. And the same as before, we don't need the accumulation, so I'm just going to remove it over here. And now, instead of pattern matching on the sat, we're going to pattern match on the stack. I'm going to say, okay, so if the stack is empty, right, then it's false. Otherwise, if the stack is not empty, then what we have here is not left element and right. What we have here is some set on the top of the stack, right? And we have other sets on the stack, right? And now we match on the set, right? So now I'm going to say sat match, put that whole thing in there, right? Okay, so now we have two cases, the same as before. If the sat that is at the top is already empty, then it means that there is no need to push anything further on the stack, so we just need to pop the stack. How do we pop the stack? We just call loop, and we basically ignore the sat, right? So we're basically saying, okay, if it's empty, we ignore it. So let's just loop without this element, right? So this is effectively popping the stack, right? Whoops. I'm sorry, I pressed page down accidentally. Okay, so this is a pop plus obviously the JVM push and pop you know, we can't get rid of the JVM push and pops. Okay, so the other case, and this is the one that we had before as well, it's a set NonEmpty, right? And NonEmpty as always, we have left element and right. Okay, arrow to the right. So in this case, same as before, if input equals element, then it's true, right? This is, you know, the whole notion of contains, have we found it or not? And otherwise, if it's on the left, then instead of just looping on the left, we're looping with the other sets on the stack, and we're gonna push the left one on it, right? The same thing over here, but it was the right one. Right one. Also, before Scalar from refactors everything, I want to inline these two lines. So I'm just going to join these lines, and I think the refactoring is going to look pretty now. Okay, we're still looping this somewhere over here. Oh yeah, so now we can just pass in the set. We need to have an empty stack, and we need to push the set on it. It's the same thing as we did with Fibonacci. In fact, let me do that over here. Okay, hold on. Sorry, push this. There we go. All right, should be green now. It's literally the same thing as we did over here, right? So we push the n, you know, for the Fibonacci on the stack, and we push the entire set on the stack. Now again, because it was already tail recursive like to begin with, we only need the last thing on the stack, so we didn't really need to build the entire stack. But in our next examples, you know, with fold and with add and remove, we will actually you know, get some real benefits from the stack. Okay, so let me collapse these two again like that. Set flew down over there. Let's have it like this. Okay, in fact, let me bring this down a little bit, because the code is more important, right? So this is our whole structure. This is the structure that we're going to be working with today. Okay, so we're going to have some sort of loop with some sort of stack. Maybe we'll have some accumulation. I mean, obviously we will, because like in this case it was already tail recursive, so we didn't need to. But in the next few examples we will have to. Okay, so we're pattern matching on the stack. If it's already empty, which means it means that we're done, right? So we're always starting with something on the stack, and then sometimes we pop things from the stack, sometimes we push things on the stack. And by the way, this is over here, I forgot that this is also our push and the JVM push and pop, right? So we have our push over here, right? So sometimes we pop things from the stack, sometimes we push things on the stack, and in the end everything is tail recursive, because it's always the last thing. The last thing that we do is we either push something on our stack or we pop something from the stack. So this is going to be the same, the similar structure as always. So either we don't have anything on the stack, then we're done, or we do have something on the stack, and then we figure out, okay, is it the empty case? Like, what is that thing that is on top of the stack? If it's already empty, then we pop the stack. If there is something else to do, then we push things on the stack. And in the fold, we're actually gonna have a push twice, and this is what we're gonna do now. All right, so let's look at the fold, and it's over here. So in the case of empty, we just return the seed, and otherwise we apply the function to the current element, and then we fold over the right one, and we fold over the left one. Notice that we're in the sets, so it doesn't matter if we do the right branch first or the left branch first, because set don't have any interest in enforcing order, right? So what we're going to do here is we're going to inspect this. So this is as before, this is a JVM pop. In fact, let me have an enter over here, and over here what we have is a JVM push and pop, and over here what we have is our problem, push and pop, right? The problem is that we have a pop over here, and then we're pushing again, and this is the sign that it is not tail recursive. So in order to fix that, we're gonna skip this intermediate step, because I don't want to waste your time. So I don't want to rewrite this to the loop case first and then to do the stack. We're just gonna go straight to the loop version with the stack. Okay, so I'm gonna in fact, I'm not gonna copy anything. I'm just gonna call this fold, I'm gonna call it fold original, right? I think this is how I called contains, right? Yeah, contains original, fold original. Okay, so it's not an override anymore. Okay, this is the only thing that I will duplicate. I will duplicate this line. Okay, so we're gonna have that. It's gonna be called fold, and now it's an override again. Okay, so the idea is as before, right? So we're gonna have an tail recursive method called loop over here, right? And it will get a stack, which is a stack of sets of element, right? And it will have other things, and it will return the result. That's, you know, that's how this whole thing works, right? So we're just going to do that, and it will match on the stack somehow, and we're going to finish writing it a bit later, right? So before, we're going to call loop the same thing with an empty stack, and we're pushing this, right? So this structure is the same as was contains. See, we're doing the same thing as before, and you know, this is how it looked before, but this time we'll actually need an accumulation. Okay, so over here we will actually need an accumulation. What are we accumulating? Well, we're accumulating the result. And now the code is almost like a mechanical transformation, except for one tiny thing. So if it's an empty stack, then we just return whatever has been accumulated before. And this is pretty much the same as what contains, but with contains there is no accumulation, right? But this is the first thing we do. If it's empty, then, you know, we're done, right? So this is the JVM pop. All right. So the next thing we're going to do is, in fact, let me copy paste this from contains. So I'm going to copy paste that over here. There you go, right? Because this is exactly the same thing. So it's either set or the other sets on the stack, right? So we're gonna do set match. I can literally keep copy pasting from the top. So if it's an empty set, then there's nothing more. There's no need to push anything. So we loop, and we're basically popping, right? Remember, we're ignoring this. Hold up, there's an arrow missing. That's why the syntax highlighting is broken. So we're ignoring this, which means we're effectively popping the stack, right? And we're just passing the accumulation along because it means that we don't need to do anything, right? So this is the same as was contains. This is a pop from our stack plus the JVM push and pop. There we go. Now the next case is more interesting. This is this case. Oh, and by the way, I said that I will. Oh no, this is. Yeah, this is the one that I want to copy because, as I mentioned, I want to distinguish between stack.empty and set.empty by prepending the pattern matches with set or stack, right? So in this case, we need to actually look at the original fold and understand what is happening. What is happening is that we have a push twice, right? We have to go to the right one, we go to the left one. And this is one of those things that is easy to understand, but it's actually very, very hard to come up with, right? So in this case, we're going to loop, and we need to push something on the stack, right? We need to push something. We're going to do that part later. But in the end, we need to modify the accumulation by actually applying the function to the element and to the ACC. Oh, it's the other way around. ACC and element, right? So this is going to be basically that line. So we're still calculating the current result, and you know, we could actually have it like this as well, right? So we could have, in fact, let's have it, right? So let's have it like this. It's the same as before, right? It's just ACC now instead of this, right? So the whole point of tail recursion is that we always go like only forward, right? So we are at this element, and whatever situation we're in, we can already process this element, right? So we can already calculate the current result. What we just need to do is we need to remember that we also need to work with left and work with right. So what we do is we take the other sets on the stack, whatever is remaining, and we're making sure that the right one will be processed as well, and that the left one will be processed as well. And the order doesn't matter, the same as before over here. You know, we did the right one first and then we did the left one. We could switch them, but it doesn't really matter because we're in the sets. And I believe, unless I made some spelling mistakes, this is still the valid implementation of fold unspecified value parameter ACC. Oh yeah, so in the beginning, the ACC is the seed. And there we go, everything is still green. Let me just inline that so that you see that this is still small. And let me also add a comment over here saying that we have a push twice. And as always, we have a JVM push and pop. So again, this I hope that this is, you know, relatively easy to understand, but it's very, very hard to come up with. In fact, it took me quite a few hours to remember how that thing was working. Because if you look at contains, for example, ignore the fact for now that it is already tail recursive. The thing about it is that in any branch, it either calls the loop once or it doesn't call it at all. But whereas with fold, there's a tricky you are in the same branch, you're calling fold twice, which is why we ended up having 2 pushes on the stack. As I said, coming up with that is a bit hard. And as I said, just to have some proof, we can push the left one first and then the right one, and it shouldn't matter, right? Because we have sets. All right, so let me revert this. There we go. And the next thing that we're going to do is we're going to do add and remove. They will be very, very similar. So we're basically just going to do one, and then we're going to copy paste that to remove and change 1 or 2 things. There's a tricky part about add. Let me actually scroll down so that I can show it to you. If we just start blindly converting it, like mechanically converting it to the loop and then converting it to the loop with a stack, we're going to run into an interesting situation. The thing is that with the, let's call it natural recursive algorithm, what is happening is that add is actually doing 2 things instead of 1. So the first thing is it finds the place where to put the element, right? So it knows if it should go left or right, or if the element already exists, and then it actually rebuilds that that branch of the tree, right? But the problem is that the finding part is happening top to bottom, right, while we're traversing the tree to bottom, but the rebuilding part is happening bottom up, right? So we're constructing the very last element, which is this one, and then we take that and we add it to the left or to the right. So the first thing that we will do is we'll actually implement that, and we'll see that it is broken. And this is, by the way, the test that I added that that wasn't failing. As always, I'm going to copy that. Should I copy that? Yeah, I'm going to copy that. So I'm going to copy that. I'm going to call it add original, like that. Paste it over here. Let's clariform inline everything properly. All right. So as always, we're gonna have braces around this thing, right? So we're gonna have a loop. It's gonna take a set of elements. We're not doing the stack thing first yet, right? So we're gonna do set of super, right? So what we're accumulating is another set, right? Add is producing another set, right? And it's still tail recursive, so let me actually copy paste that, scroll down again. This is where we just were, put it over here, right? So what we're producing is a set of super, right? So we're gonna do, instead of this match, we're gonna do set match, like this. I'm just gonna remove that line. This means that we need to start the whole thing with this, and the accumulation is going to be whatever was here, right? So now if it's empty, we just return ACC. Otherwise, we're just returning non-empty. And in this case, we're just gonna loop with the left, and now we're gonna copy. So it's the same part as over here, equals ACC. Right, so we're blindly doing that. And now we just need to switch it to the right. There we go. So now it should compile, but it shouldn't work. Right. So as we see, 7 tests are failing, and again, it's because right now when we convert that whole thing, notice that it compiles, right? So it is tail recursive, right? But the problem is, as I said, finding the place is top down, but rebuilding is bottom up. This is the difference between the original implementation and this one, because in the original, I explained it sort of wrong before. Like the original implementation is smart enough to remember where it was and to backtrack, but this one is not. So this one is while you're traversing, you have already built the part of the tree, but you're building it the wrong way. So you're ending up with a really small tree. It's kind of hard to explain. Basically, play around with this. So the solution to this is to have 2 loops instead of 1. So we're basically splitting, gonna rip this algorithm in 2 parts. The first part is going to be finding the path, and the second part is going to be to follow the path and rebuild the set. So in order to do that, we're going to need a helper class. But before that, we're going to throw out this whole thing, and we're going to have the skeleton of the algorithm, right? So the skeleton of the algorithm will be this. There will be a way to figure out the path by giving it the set of elements, which is going to be this, right? So somewhere at the bottom, we're going to call path was this, right? And what it will do, it will calculate a path of these elements. We don't have that yet. We're going to add it in just a second, right? So we're going to throw an exception over here. Okay. In fact, maybe let's switch to compiling. Compile like that. Okay. So now it's still compiling because I didn't save the file. So we're going to have the path, and then we will rebuild the set based on the path, right? So we're going to have the path of element, which is coming from here. Okay. And now we'll be able to construct a set of super like that. So as soon as we have the path, we can rebuild it like this, right? So this is the skeleton, and now it should compile. It shouldn't compile because we don't have the path. Okay, so what we're going to do now is we're going to go to the bottom of the file, which is our object set, right? Like this. So we're going to add something to the object set, right? So we're just going to add something that we're basically going to hide from the rest of the world. And what we're adding is this private type path, which is just going to be a stack of direction of the element. And direction is going to be a teeny tiny private sealed trait. Direction, okay, direction of element. And we're going to try to optimize this as much as we can so it extends any. And we're going to have 3 implementations. Private case class left, which will remember that we have to go left, which takes in a NonEmpty, which is a NonEmpty set of elements, right? And it extends any val with direction of element, right? So we're extending this. So then we're going to have 2 more of these. This one is going to be called center because this is going to be basically, okay, we found the element, right? And this one is going to be right. So they all look the same, right? But one is left, one is center, one is the right. So let's see, it should compile now. Yes, so it compiles now. So now let's actually implement this. So in order to implement this, we're still going to use our recipe, right? We're still going to start with a loop, and it's going to be a tail recursive, and we're going to have a stack in there somewhere, right? So the path is a stack. Okay, so let's start. Let's start with the path. So we're going to open that, and we're going to have some sort of loop in there, right? It's going to be tail recursive as before. Right, and what it will take is the set, right? Notice that we're shadowing this variable, right? Okay, so set, and it's going to take the path. This is basically the accumulation of the path, right? So usually we call this ACC. I'm sorry, ACC, but this time we're just going to call it path. Okay, so and as always, it needs to calculate the path of element, right? So, and it will pattern match on the set as always. Okay, we're going to finish it in a second. So we're going to start the whole thing with the set that is coming from here, right? Maybe I shouldn't overload the value, overload this variable. Hold on, let's do s. Okay, this is going to be a bit more more easy to understand. Okay, and we're going to start the whole thing with stack.empty. Now rebuild will pattern match on the stack, right? And it will be, because path is basically a stack, right? So remember, path is a stack of directions, right? So rebuild will understand, okay, so if the stack is empty, then it means that that this element either already exists or that the set is empty, right? And in both of these cases, it will know what to do. Okay, so this is the beginning, right? So the empty path and our current set. Okay, so as always, we're going to say, okay, so if it's an empty set, right, then just return the path, which is a JVM pub. Okay, and otherwise, if it's a non-empty, which is a set dot non-empty, right, left element, right. Okay, the arrow to the right, and we have the same as before, right? So basically we can we actually copy that? Well, let's try to copy that. Let's do that, right? So we can copy that because it's always the same, right? So if input is equal to the element, then we have our path, which is basically our accumulation, which is our stack, and we push on it the center, right? We say, hey, we found that thing, right? Right? That means that there's no need to add anything. but rebuild will pattern match on the path, and it will understand that if there is a center, it means that is basically done, right? So we're just pushing on the center, which is a push plus JVM push and pop. Okay, so in this case, let me do that. It's gonna loop with the left, and it's gonna take the path, and it's gonna push left, NonEmpty. Okay, so instead of actually rebuilding the SAT as we were doing before, we're just building the path. Okay, copy that, bring it down, replace this left with right, and this left with right, and now we're done. Okay, except for actually adding this push plus JVM push and pop, right? And the same one over here. Also notice that because we're basically splitting this algorithm into two pieces, one will only push things onto the stack. You see our pushes, right? Push, 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 nothing pops that stack. And rebuild will do the opposite. It will not push anything, it will just pop it. Okay, so let's start implementing the rebuild function, and the rebuild function as this one will have a loop, same as before, loop, right? And it will start the loop with the path of element, and I'm using the path here. I should probably use P over here. Okay, so path and the accumulation of the set of super, right? And it produces the set of super. This is its purpose. It's to build this set of super, right? So we're going to do P match, okay, and it's going to be tail recursive as well, tail recursive, and we're going to start the whole computation of rebuild with a loop of path that is coming in over here. And an important part, this is the thing that SAT was doing in the very beginning, right? So in the add case, hold on, where is it? This one. This is where it comes from, that part. Okay, so basically it will say if the set is empty, then this is going to be the new set, or if the element is already contained, then when you're rebuilding the set, just rebuild it was the same thing. Okay, so let's go here and we do this case stack dot empty. Notice that over here we pattern match on the set, and over here we're pattern matching on the stack. Like this is more close to the thing that we were doing before, was Fibonacci and was contained and was fold, right? So we're pattern matching on the stack, and we always know, okay, if this is the last thing, then we're done. This is the JVM pop. Okay, and the next thing is going to be stack dot NonEmpty, same as what I was doing before, but now we have directions. Like usually we have like sats and other sats, but over here we're going to have direction and other directions on the stack. Okay, so, and this is where the tail recursion comes in. We're just calling the loop once. Okay, just calling the loop, and the path is going to be other directions on the stack, right? So this is the pop, right? Remember how I said that when we're building the path, we're just pushing things on the stack, and over here we're just gonna pop. This is why we have only one loop where we just pop. We're never gonna push. Okay, we pop, and now our accumulation is going to be the direction, which is this thing over here, right? That thing that is on the top of the stack, and we're gonna match on it, and now we're gonna figure out where to put it, right? So now we're gonna figure out if it's left. And that might not work because I might need to import something. I'm not really sure. We'll figure it out. Okay, so if it's not empty, I'm sorry, not if it's not empty. We actually kind of always know that this is not empty, right, over here, because whenever we push something on the stack, it's always a non-empty set. See, and when we're constructing the center, it's a non-empty. We're constructing the left, it's non-empty. Constructing the right, it's a non-empty. I'm not even sure. Have we encoded that into yeah, into here? Yeah, I forgot to say that. So we only need to do this for non-empty sets. Okay, so let's scroll up over here. Okay, so if it's the left one, then we actually do that thing that we tried in the naive implementation, right? We're gonna go to the non-empty, and we're gonna copy that, and we're gonna say that left equals ACC, right? Because we know that we need to put it on the left. Okay, so this is the JVM push, and pop, right? So there's no pushes on our stack. Okay, so this is the left, and we're gonna have the case center, not empty. This means that there's no need to do anything, right? So we're just gonna return it the same as before. And the same as before what we had in the original version, this one, right? So basically we're done. Where are we? Okay, this one. Okay, so now I can just copy this one. Okay, there's a comma here. Why is there a comma here? Why did I put a comma here? There shouldn't be any comma. Okay, so this one is the right one, and this is also the right one. And unless I made some silly typing mistakes, there we go, reassignment to val. Okay, I called it p and not path. All right, so now it compiles and we're actually done, right? So again, if I collapse these, this is our whole algorithm, right? We're building based on some path, right? The way we calculate the path is we're looping through the set and we're just figuring out, should we put it to the left, should we put it to the right, or we shouldn't put it at all. So I just called it center, but we might have called it, match or something, right? So, and then rebuilding, it takes that thing and strips off parts of it all the time, right? It goes down that stack, right? It pops them all the time, and then it figures out, okay, so at this point in time, I should have went left. Therefore, I'm going to copy, I'm going to replace the left element with whatever we have accumulated before, right now, right? And if it's the center, then I don't need to change the accumulation at all. And if it's the right, then I'm going to put it on the right. And now, if I switch to running the tests, it should still be fine, unless I made some horrible mistake somewhere. Yep, it's fine. So we have the original version. All right, so the last thing that is left to do is to do the remove, and the remove is going to be exactly the same. So I'm going to copy the whole thing, and the remove have been the same from the very beginning. There were like only two subtle differences. So this is the remove original then, okay? Right. So if you compare it with the original add, there's a difference in here, and there is a difference in here, right? So over here is that. I just know it. I'm not going to scroll up. I just know that in this part is going to be in this case, and in this case it was always just returning non-empty, right? So if I paste that thing over here, and let's do a big surgery, I'm just going to call it remove. Notice the figuring out of the path is not changing at all. Like this could be actually factored out. Okay, and the rebuilding, it's going to start with an empty, and over here I believe it's going to do left union right, the same as it did before, but now this means that we need to deconstruct that thing. So we're going to do set dot non-empty left. We don't care about the element. Right. So in fact, in this version, it is actually even more clear that we're removing the element by not using it over here. Okay, so I believe that's the only two changes that we needed. Refactoring took place. Yeah, everything is still green, so we're pretty much done. All right, so we're pretty much done with everything that I wanted to talk about. Today, what we're going to do now is we're going to commit that whole thing as is, so that you see the original version and the transformations as well, because it was probably not so easy to follow. So what I'm going to do here is I'm going to exit, and I'm going to do git status. Notice that we added Fibonacci, right? But I believe if I don't explicitly add everything, it will just not add Fibonacci, because I don't want to commit the Fibonacci example, or maybe I should. Yeah, why not? I'm gonna commit the Fibonacci example as well. Yeah, why not? Yeah, I'm gonna commit the whole thing. Easy. Add everything. Git commit -am. This is still video 13, and we're gonna call it, okay, so advanced tail recursion, and I'm gonna say stack. Okay, so we're gonna do that, and we're gonna push. And by the way, we're not done with the whole tail recursive topic. We have quite a few videos coming up where we're gonna do basically the same transformation, but without using the stack, but with using something more fancy. All right, so the last thing that is left to do is to look at our commits. So let's look at this one and this one. So the first one is just a refactoring. So we changed the manual creation of elements to the call to the copy method. And in fact, let me zoom in a little bit. Okay, We removed the on top of, we fixed the spelling mistake, we added a test, and we removed the print line. And this is the advanced tail recursion where we added the whole Fibonacci example. And we played around with contains, we played around with fold, and we played around with add, and we played around with remove. And that's all I got for you today. It's been Vlad, devinside.com. Like this video if you did, subscribe if you want to improve the developer inside you, and most importantly, take care.